In this video, we're going to be looking at algebraic curves and figuring out what's going on with these in preparation for learning about GAPA codes. So, for the definition of an algebraic curve, let K be a field, and suppose we're looking at polynomials in two variables, so in x and y, that have coefficients in k. If we've got a non-zero polynomial, f of xy, then the algebraic curve attached to f to find over k is going to be the set of zeros of that polynomial. So when we're talking about an algebraic curve, we're really talking about the set of solutions to a polynomial equation. So really, an algebraic curve is just the set of zeros of a polynomial in two variables. So for example, if we look at f of xy equals x squared plus y squared minus 1 over r, then we're looking at the set of points where x squared plus y squared minus 1 equals 0, and we can recognize that as the unit circle in the plane. So that's our algebraic curve associated to that polynomial. If we look at x cubed minus x squared plus y squared over r, then we get our curve as this little loopy thing. So once again, the zeros of that polynomial. So because we're working with codes and we want to be able to use finite fields, we're going to need to know what an algebraic curve over a finite field looks like. Figuring out points of a curve can be really tricky over kind of weird fields other than the real numbers. The book goes through a few examples of this. There's not really one set way to do this. You just kind of have to try different methods for different polynomials and hope that something works out. So for a couple of examples here, we're going to go through and find all f5 points of this polynomial, or this equation 0 equals x squared plus y squared. So in this situation, we're going to look at kind of what are the possibilities for squares here. So if we can figure out what this first part can be and what this second part can be, then we can look at how we can add those two parts together to get 0. So we'll start by looking at the squares mod 5 and see that we get 0 squared equals 0, 1 squared equals 1, 2 squared equals 4, 3 squared equals 9, which is 4, and 4 squared is 16, which is 1. So we see that our possible squares are 0, 1, and 4. And so when we're adding together two squares and getting 0, we could either have 0 plus 0, 1 plus 4, or 4 plus 1. So looking at kind of all of the possible combinations that give us those, we've got our points are 0, 0, 1, 2, 1, 3, 4, 2, 4, 3, and 2, 1, 3, 1, 2, 4, and 3, 4. So those are all of the f5 points of this algebraic curve. Now let's look at finding all f3 points of this equation 0 equals x cubed minus x times y. So something kind of strange happens here, which is that by Fermat's little theorem, we have that x cubed is congruent to x mod 3 for all points in, or all numbers in f3. So for 0, x equals 0, 1, and 2. So that's going to mean that when we plug 0, 1, or 2 into this, we are going to get 0 no matter what. So that means that all points are on the curve. So we have all points over f3, we've got 1, 0, 1, 1, or 1, 0, 2, 0, 1, 0, 1, 1, 1, 2, 1, don't need 3, 2, 0, 2, 1, and 2, 2. So in this case, this polynomial, although it doesn't seem like a trivial polynomial, we actually get all points on the curve as zeros of that polynomial. In the next video, we'll look at singularities of curves, so figuring out what it means for a curve to be kind of smooth or not have any corners, or issues like that.